When you pick up a syllabus from a place like MIT, you expect something incredibly dry,
Right.
something like advanced linear algebra.
For microarchitecture of silicon systems, something that puts you to sleep just reading the title.
Exactly. But the material we're looking at today, honestly, the title sounds like a YouTube tutorial from a 20-year-old life coach.
It does have a certain aggressive optimism to it, doesn't it? Very internet native.
How to AI almost anything. I mean, that is the actual title of a course. It's running right now, spring 2025, at the MIT Media Lab. And I just saw that and thought, okay, is this clickbait?
It sounds like it, but, don't let the marketing fool you. This isn't some get-rich-quick with ChatGPT seminar.
Right.
It's a graduate-level course taught by assistant professor Paul Liang. And despite the fun title, the ambition here is actually pretty technical. It's trying to solve one of the biggest bottlenecks in modern tech.
Which
The
is
huge disconnect between the digital brain and the physical world.
Okay, that makes sense. Because for the last couple of years, when we say AI, we really just mean large language model. It's text in, text out.
Maybe a generated image if you're lucky.
Yeah. But this course is arguing that if you want to AI anything, and the emphasis is on the anything, you have to get out of the chat box.
Exactly. The whole core concept here is multisensory intelligence. And that's a really significant pivot from where the industry has been focused. The old AI, and it's wild that we're calling tech from 2023 old.
It is wild.
It lived on a server. It processed language. But the world isn't made of language. It's made of photons, sound waves, physical forces, chemical signatures.
And logical signals.
Right. And this course is all about building systems that can ingest that messiness and actually make sense of it.
So practically speaking, what does that list of inputs look like? Because I'm looking at the modalities in the course overview, and it is a laundry list. It's not just camera and microphone.
No, it's exhaustive by design. They list specific technical sensors, radiology, so reading things like X-rays or MRIs, histology, which is the microscopic study of tissue structure.
Which is already a huge leap from, write me a poem about a cat.
Right. But then they add mobile data, wearables, gestures, and even emotional states.
Emotional states, that one stopped me. How do you treat emotion as a hard data input?
Well, see, that's part of the multisensory puzzle. You don't scan an emotion directly like a barcode. You infer it from a combination of other inputs.
Ah, okay.
So the cadence of the voice, maybe the flush of the skin, a biometric spike from a wearable. The argument Professor Lang is making is that true intelligence requires synthesizing all these disparate streams at the same time.
So you can't understand the emotion if you only have the transcript of what was said.
Exactly. You need the audio, you need the visual, maybe even the heart rate data.
That word synthesizing feels really key here. The stated goal in the intro slides is human-AI symbiosis. Now, I usually get a little nervous when I hear symbiosis in a tech context.
I get that. It can sound a bit invasive.
Yeah, but that's not what they're pitching here, is it?
No, not at all. In this context, symbiosis just means an alignment of capabilities. It's about the AI understanding the human's context well enough to be actually useful in the real world.
Okay.
There's a slide that explicitly contrasts analyzing data with real-world interaction. If an AI just analyzes data, it gives you a spreadsheet, a report. But if it understands real-world interaction, it can anticipate your needs because it sees what you see and here's what you hear.
So it's the difference between a search engine that you have to query and a partner that works alongside you.
Precisely. They visualize this as the intersection of four huge industries: health, smart cities, IoT, and robotics. And the whole premise is that these fields have been kind of stuck in silos.
Because they couldn't process the same data.
Right. They lacked a unified way to process all this sensory data. The idea is if you solve multisensory intelligence, you unlock all of them at once. You don't just get better robots, you get better hospitals. You get smarter cities, all using the same underlying logic.
Let's get concrete. Because unlocking industries is a great slogan, but I want to know what this looks like in practice. The lecture slides have some very specific, almost quirky examples. I want to start with the peanut butter.
The peanut detector, yes. This is a classic example of what they call AI for physical sensing.
And paint the picture for us. We are not looking at a robot chef making a sandwich here.
No, not at all. The image shows a regular jar of peanut butter. And it's sitting next to this custom electronic circuit board. It looks like a breadboard with exposed wires and a little sensor on it.
And a little screen.
And a little screen, yeah, an OLED screen that's displaying a graph. And the text? Peanuts not detected.
Which implies it's sniffing the air, basically. And if you open that jar, the text would change.
That's the idea. It's an electronic nose. Now think about why this is in a computer science AI course. Normally, sensing chemicals is a chemistry problem. But here, they're treating the chemical signature of allergens as just another data stream like text or pixels. The AI is trained to recognize the pattern of peanut molecules amid the noise of the rest of the room.
And the application is it's obvious, it's safety.
Immediate invisible safety. It's not an AI reading the ingredients label for you. It's an AI sensing the physical reality of the air to prevent anaphylactic shock. And that is a fundamental shift from information processing to physical sensing. It makes the invisible visible.
The other example that really stuck with me, and this one felt a bit more aggressive, was the robot arm. There's a sequence of photos labeled resilient robot.
This is a demonstration of robustness. And robustness is pretty much the holy grail for robotics right now.
So what are we seeing?
You see a robot arm, it's trying to do a precise task like stacking a box. And then in the middle of the movement, a human hand just comes into the frame and physically shoves the arm.
It's labeled external force. And it's not a gentle tap. They're really pushing it off course.
And in a traditional, a hard-coded robotic system, that's a catastrophic failure. The robot generally knows its coordinates, x, y, z. If you push it, it's now at x plus 5, but its internal logic thinks it's still at x.
So it's going to mess up.
It's going to try to finish the move from the wrong starting point and probably smash into something or just lock up.
But this one doesn't.
No, the slide shows it recovering. It feels the force, it adjusts its trajectory. It's essentially rewriting its path on the fly, and it completes the stack.
There's another image in that same sequence called camera occlusion. Somebody just stands right in front of the robot, blocking its view.
And yet, it still finishes the job. This is the multisensory magic at work. I mean, if I close your eyes, you can still touch your nose.
Yeah, I know where my hand is.
Proprioception, exactly. The robot is likely combining vision with its own proprioception internal sensors in the motors telling it how the arm is positioned. When the vision goes dark, the AI just weights the proprioception data higher and keeps moving.
So it's not blind.
It just switched senses.
That adaptability is what makes it street smart instead of just
lab smart. Yeah. That's the prerequisite for having robots in our homes.
Yeah.
The real world is full of occlusions and external forces. Kids, pets, whatever. If the AI can't handle a shove, it can't be in your kitchen.
I want to pivot now to the sector that seems to have the most immediate potential for this, and frankly, the one that feels the most personal: healthcare. The course highlights a specific research paper, Day et al., Clinical Behavioral Atlas.
Yes, and it's worth noting that David Dye is actually a teaching assistant for this very course. So the students are learning directly from the people building these things.
The framework they propose is called holistic health. And looking at the diagram for it, it really highlights just how narrow our current medical diagnostics can be.
It really does. The model proposes 3 pillars of health data. The first is physical. That's what we're used to.
Right. X-rays, tissue samples, blood tests, the hard data.
But then it adds social and emotional as equal pillars.
And this is where the multisensory part becomes absolutely critical. How do you measure social health? The model suggests analyzing dialogue and networks. How do you measure emotional health? By analyzing voice prosody.
The tone and rhythm of speech.
And wearable data that might show stress responses, all these different signals.
It sounds almost intrusive, but at the same time, it's exactly what a good human doctor does intuitively.
That's a great point. A good doctor notices if you sound depressed. They asked about your support system.
Exactly. But a doctor sees you for 15 minutes, maybe once a year. This AI model implies a continuous 360-degree view. It's trying to build a clinical behavioral atlas. So it's not just detecting a tumor, which is the physical part.
Yeah, it's more than that.
It's detecting that the patient has withdrawn from their friends. That's social. And that their voice markers indicate high anxiety. That's emotional.
And treating the whole person requires understanding how those things connect.
Right. The implication is that health isn't just the absence of disease in a tissue sample. It's a complex, dynamic state. And you can only see that state if you have sensors that can listen and watch, not just measure.
Okay, so we have the robot that can feel, the sensor that can smell, and the doctor that can listen. The last example is the agent that can shop.
It sounds so mundane compared to saving lives, but from a computer science perspective, the interactive agent is a massive, massive challenge.
This is from the segment on digital automation. The prompt given to the AI is, Purchase a set of earphones with at least 4.5 stars in rating and ship it to me.
Okay, think about what that actually entails. You're not asking the AI to search a structured database where everything is neatly labeled. You're asking it to navigate a live website built for humans.
The slide shows a one-stop market interface, and the AI has to scroll, it has to read text, it has to figure out which pixels are the filter button.
It breaks the whole process down into this loop: instruction, feedback, actions, and clarification. So the AI takes the instruction, it performs an action like clicking the electronics tab, it gets feedback, the page loads, it sees the new page, it scans for earphones, it filters by 4 stars and up, it's browsing.
We've had shopping bots before, though. What's actually new here?
Well, the old bots usually just hooked into an API, a structured data feed from the store. They were just exchanging text code in the background. This AI is actually looking at the screen.
It's seeing the website.
It's seeing it, which means it can theoretically navigate any website, even one it's never seen before, just like a person can. It's interpreting the visual layout to understand how it works.
It brings us back to that idea of the generalist. If you can see and read, you can do almost anything on a computer.
Exactly. It's the digital equivalent of that robot arm. It's an agent acting in an environment, perceiving changes, and making decisions. Whether that environment is a warehouse or a website, the underlying intelligence is becoming surprisingly similar.
I want to step back from the specific tech and look at how this is being taught, because the structure of the course itself seems to tell a story about where the field is going.
It's a very deliberate narrative. The syllabus is split into 4 modules that pretty much recap the evolution of modern AI.
Module 1 is Foundations, weeks 1 to 4. That sounds like standard stuff.
But even there, notice week 4, Spatial Hierarchical Epoch. They are planting the seeds of space and structure right away. They don't want students thinking of AI as just a cloud of numbers.
They want them thinking about geometry from the start.
Right. Then module 2, Foundations of Multimodal AI. This is where the senses really come in.
This is the core toolkit.
This is it. They talk about cross-modal transfer, which is a fascinating concept. It basically asks, can I learn something through one sense and apply it to another?
Give me an example of that.
Okay, imagine you've never seen a tennis ball, but you're holding one in a dark room. You feel the fuzz, the curve, the seam. Then the lights come on, and you see it across the room. You recognize it instantly.
Because I transfer the tactile data to a visual understanding.
You did, and that is extremely hard for computers. A computer usually learns images of balls and texture data of balls as 2 totally separate things. Teaching it to bridge that gap is key to that symbiosis we talked about.
Then we move to Module 3, Large Models.
Scaling up. This is where they bring in the heavy hitters LLMs, but adapted for this multisensory world. Large multimodal models.
And finally, Module 4, Interactive AI.
Which brings us right back to the robot arm and the shopping agent. It's the culmination. First you learn the math, then the senses, then the scale, and finally you put it out in the world to interact.
I also noticed the student roles are unusual. They don't just sit and take tests. There are scouts and synopsis leads.
It's a very modern way to teach. A scout is responsible for finding new papers.
Which implies the syllabus isn't set in stone.
It implies the field is moving too fast for a fixed syllabus. By the time the professor writes the lecture, a new paper might have dropped that changes everything. The students are basically crowdsourcing the curriculum in real time.
And the synopsis lead merges notes. But the assignment that really caught my eye is the academic researcher exercise.
I love this assignment. The prompt is, and I'm quoting here, propose an imaginary follow-up project, only possible due to the existence and success of the current paper.
Imaginary follow-up project.
It totally prohibits rote memorization. You can't just report on what the paper did. You have to understand it so deeply that you see the implications. You have to stand on the edge of the research and look forward.
It's training them to be inventors, not just engineers.
That's it. Now that we know X is possible, what does Y look like? That's the fundamental question of innovation.
So listening to all this, I'm getting hyped. I'm thinking, I want to take this course, but then I check the prerequisites. Python, deep learning basics. It's heavy technical stuff.
It is. You can't build these systems without the math and the code. But did you catch the third requirement listed in the learning objectives?
I did. It was the curveball. Bring external, non-AI domain knowledge about your problem.
That is the most important sentence in the entire document for your listeners.
Explain why.
Because it's an admission that AI cannot exist in a vacuum. If you want to use AI to solve a problem in urban planning, the Python code isn't enough. You have to understand how cities work.
If you want to solve a problem in biology, you need to understand the tissue samples.
Exactly. The AI provides the how, but the domain expert provides the what.
Mm.
We're moving into an era where the most valuable people won't just be the ones who can write the best transformer architecture from scratch. It'll be the people who understand the specific, messy, real-world problem deeply enough to know which sensors to use and what the AI should be looking for.
So if you're a doctor or a mechanic or a musician, you aren't obsolete. You're actually the missing piece of the puzzle.
You are the one who defines the anything in how to AI. Almost anything. Without your domain knowledge, the AI is just a powerful engine with no steering wheel.
That is a much more empowering view of the future than we usually get. It makes you feel like an active participant.
It's collaborative. That's the symbiosis. It's not AI replacing the expert. It's the expert wielding a new multisensory tool.
So we've covered the shift from just text to multisensory. We've looked at the peanut sniffing sensors, the robots that can take a shove, the doctor that listens to your tone of voice.
And the agents that surf the web. It's a picture of AI that is finally stepping out of the screen and into our actual lives.
The vision is huge, creating human-AI symbiosis across scales and sensory mediums. And based on the syllabus, it feels like this class at MIT is right on the cutting edge of making that happen.
They're building the toolset for the next decade.
Now, before we wrap up, I want to leave our listeners with a thought experiment inspired by that academic researcher assignment.
Let's hear it.
The class asks students to propose a project based on a new capability. So here's the question for you, the listener. If you could give an AI one new sense, something beyond a camera or a microphone, to solve a bottleneck in your specific line of work, what would it be?
That's a great prompt. Would you give it a thermal sense to find leaks in insulation? Or maybe a network sense to visualize data flow in a server room?
Or maybe a bureaucracy sense to detect which form is going to get rejected before you even submit it.
No, that is a billion-dollar startup idea.
Just think about it, because as we've learned today, if you can define the sense, you can probably AI it, and if you can AI it, you can change how that problem is solved forever.
The technology is ready. It's just waiting for the right problem.
Thanks for diving deep with us today. Keep your senses open,